All right, let's talk about relational databases. Right, so we'll talk about some of the most basic concepts, records, some of the attributes of all databases, about multi-user access, memory management, data models, and how they're represented in conceptually, physically, and logically. So, what is a database, right? So, any data collection, we could generally say that it's a database. And it's really, relational databases has been the most common way that we've been using for the last couple of decades. They very well lowered the bar of being able to understand on how or visualize how is it that we can store data. It's a very simple concept of how to think about data in the form of rows and tables, and then relate each record with other records using these indices or fields that refer to each other. Certainly, it's not the only way. There's plenty of other types of databases that allow you to capture real-time data or spatial data or hierarchical data or object data representation. So, but relational databases has nevertheless been the most common and will be for quite a while. But it's not the only one. Um, um, in all the databases, typically we think of records as a collection of related fields or data types that describe a particular concept, whether they describe an employee or student or course or section, and all the different attributes that describe that one concept. And usually we think of all the instances of students or all the instances of employees or all the instances of courses as being a collection of tables or a more generic data set, right? Um, and uh, and we usually refer to them as records. And in other databases, we might use other jargon, right? We might say that it's a document if it's a non-relational database, but it's basically the same thing, a record, right? And different databases might have different jargon to refer to the same thing. And each concept will have a set of attributes that describe that particular concept, right? Whether it's a student, might have a username, first name, last name, their graduating year. Um, if it's a department, the name of the department, the course, the section, and the enrollment. Which professor is teaching what section, and whatnot, and what student got what grade in which section. And you'll notice here there's a mixture of some data that is natural, right? That describes the actual concept, such as a student might have a first name. Will have the year that they're graduating. That's actually actual data, right? Actual data that describes the student. But then you have other data in there that doesn't seem very natural. This SID thing and DID and CID. What is that, right? And those are peculiarities or something that is circumstantial to the type of database that we're choosing to study. In this particular case, it's a relational database, right? And the only way to relate or to describe that this one particular instance of piece of data is somehow related to that other piece of data over there is through these fields, this nomenclature or this that we all agree that if I have a value of unique student or unique department, that they could refer to each other, right? That somehow the section can refer to the course that it belongs to, by making sure that the value of the course ID refers to some unique value of some course, right? But again, that's only a peculiarity of the data infrastructure that we're using, relational databases, right? If you use other alternative ways of representing them, like XML, then there is no need for these unique identifiers, right? Instead, in XML, you would perhaps put a parent. You would create a parent-child relationship between these data points by using the hierarchy, right, where children are contained within their parent, and there's no it's implied that the children are somehow related to the parent, right? There's no need for this additional foreign keys and primary keys and whatnot. Same thing in object-oriented technology. Right? Usually, you don't have primary keys or foreign keys. Right? It's implied that if you have a parent-child relationship that you use arrays or lists, right, where the relationship is implied, right, where parent-child relationship is used by implemented as collection. So in this particular case, we do have these extraneous other fields that are not natural to the actual data that we're collecting, but instead are used to establish relationships between data points, right? To establish the relationship between, and the relationship is why usually we refer to these as relational databases, right? That capture this the relationship between all these data points. So here's a toy set of tables with a school or university that's not a very big university. It has 9 students. It has 3 departments: computer science, math, and drama. It has 6 courses. It has 5 sections, and there are 6 enrollments. And this is just a toy little data set that we're going to be using throughout at least the first half of the semester. And to point out and discuss relationships, alternative ways of representing this. What if instead of doing this, we would have captured, like for instance, one of the peculiar things here that we've design decisions is that the professor seems not to be very important. Right? We're only capturing the username of the professor. There is no professor table, right? That we're capturing or that we're referring to. So, there was a particular decision that wasn't very important. And so there are all the peculiarities on how we decided to capture this, and we'll revisit this over the next several weeks. So we have a university database, we have the student records, and each record we refer to as an instance. So here we have an instance of we have 6 instances of courses. We have 9 instances of students. Presumably each one is an individual student. Notice that we're only capturing the student name, but not first name, last name, or any of that. Again, we're keeping it simple. Obviously, we'll come back to this and always point out about redundancy, other alternative ways that would have introduced inconsistency into the data set, and we'll point those out as we progress. Also, we'll point out certain entities that are only there to describe the relationships between other data points, like the enrollment records is only there to point out that a particular student is somehow related to a particular section, right? And in that relationship, they had a particular result in their grade, right? We'll come back to this in a minute. A little later, we'll say that this is an association table, right? That is associating some instance with some other instance, right? That instance number 1 is associated to instance number 3, but I want to describe that association by adding additional data, saying that, oh, by the way, that association, I have some data about it, right? I'm describing that data. Instead, if I didn't have this column over here, this field, this perhaps might have been referred to as a mapping table, right? A table that says that I'm mapping a record to another record, but I'm not describing it. I'm just saying that these are related. And so these are nuances. Since later on we're going to want to be able to describe these tables as objects, as JSON objects or Java classes, right? And depending whether it's an association or it's an association table or just a mapping table, they would be implemented completely different, right? In other representations, right? So we have to be careful with those nuances. Other things that are not here is for instance, if there would be a professor table, we might have some fields that are redundant, right? Where you might be capturing first name and last name for student, and also first name and last name for professors, right? So you might consider, says, well, you have these fields we're capturing the same information in 2 different places. How about a user table, right? And capture what what type of user as either a enumerated data type in an additional as an additional field, or perhaps if this were an object-oriented programming language, you might have a base class from where you have inheritance of two other classes that inherit from some base class. Yes. Well, I mean, those kind of concepts don't exist in relational databases, right? So that introduces all sorts of questions on how is it that you map certain concepts that are very, very common in some data representations in relational data in object-oriented programming, but are not representable in relational databases. So that would open up an entire can of worms, right? So we'll talk about those kinds of questions, right? And how is it that you would model or you would capture those kinds of data structures. We'll also come back and say and look at that there's also a relationship between courses and section. That there's a one-to-many relationship, right? Where one course might have many sections associated with it, where you might have that here. You'll notice that these two sections are associated with the same course, right? And these two sections are also associated with the same course. So there's one, usually we refer to as a one course can be associated to many sections. So there's a one-to-many relationship. Whereas in this enrollment, we might see that there's a many-to-many relationship, right? Where one student might be enrolled in many sections, but then one section can have many students. Right? So all this jargon will have to become familiarized as different strategies of modeling the structure of the data. So deciding what the structure of this data is, deciding what tables to use, how is it that we're splitting out all this data is what we call designing the database, making those kinds of decisions, and it's non-trivial. It's a non-trivial exercise, right? It might be that one of you comes up with one structure and someone else comes up with another one, and it's a fair question to say, well, which one is better, or which design is better. So we'll talk about many different principles on measuring, why is one better than another, and why one would perform better than the other. Also deciding which fields, or deciding whether the grade should live here, or maybe a separate table that has all the possible grades and everybody then refers to those grades. Perhaps that might be better. Or deciding that professors weren't important enough, that they're just a field in some table, and that professors are not worthy enough to have their own table. So yeah, why do we decide that? So other characteristics of database obviously need to be persistent. Even if you have a power failure, right, the data is still there tomorrow. You'll have multiple, hundreds, thousands of concurrent users, hitting the same data, and what are the challenges on who's reading, who's writing, who's updating, right, and what can we allow that to occur concurrently, and which things are not allowable, right? And how pessimistic we need to be, or how optimistic we need to be on certain operations. So we'll talk about those issues. Obviously, need to be accurate, that the data is consistent. That if I query, if I have a query and I have an equivalent query, hopefully the same two equivalent queries will come up with the same answer. It would be embarrassing if two queries are supposed to be the same come back as different. It says, wait, that makes no sense. So we're looking to avoid inconsistency at all costs, and there's many techniques to do that. Usable, obviously, that has to have some user interface that allows us to easily interact with, and some folks that are dedicated to maintaining the health of the system, usually referred to as the database administrators. So again, there's an infinite way of storing data. We could have just decided that we use an Excel spreadsheet, right, and just store it in just one big sheet, right, and we have all the fields are in one single spreadsheet, right, and we soon identify and find that how inappropriate or inconvenient it is that we have to copy and paste lots of data that is redundant over and over, and how much better it is when we split it up into multiple records, into multiple tables. Multi-user access. Certainly, yeah, the risk of inconsistency when multiple people are accessing the database at the same time. When you're at kayak.com and are asking, trying to get a seat on an airplane. It says there's 40 seats available, and when you are going to pay for it, actually they're gone, right? Well, how that happened? And certainly you're not the only one accessing it, and you're not the only one accessing the database and modifying it. How could we're avoiding causes that operations that might put the database in some inconsistent state, or transferring data amongst accounts that operations that need to be atomic, that are actually split up into multiple operations, but need to be treated logically as one single operation. Right? So how do you synchronize multiple databases or multiple updates into multiple records, so that you never leave the database in inconsistent state? Either using some kind of semaphore or some synchronization mechanism where you have certain operations be blocked while certain operations occur, depending on if everybody's reading, or maybe somebody's writing while somebody's reading, and make sure that nobody's reading bad data. We'll talk about that quite a bit when we talk about concurrency. Databases need to be able to identify when something went wrong, right, and be able to backtrack its way into a consistent state. Roll back any problems that might have occurred, we'll either following a log of what the updates were, so that you can undo those changes to get back into a consistent state. Yeah, a lot of transaction. We'll talk about transactions quite a bit a little later. Authentication. We also databases need also to be able to manage who has access to what. Even though I might know who you are, I also need to have what are you allowed to do, right? That you only might have access to a certain set of tables or certain set of views. So depending on those privileges, databases need to be able to enforce those privileges. So usually they provide some mechanism to doing authentication and authorization. Also memory management. Usually the databases will provide some kind of interface or client that allows users to interact with data that might be several terabytes, huge data sets, but obviously, no PC or machine is able to represent all that data all at once. So usually, whatever data you're looking at it's only going to be a small sliver of the actual data that is stored in the file system. So these databases need to be able to manage the cache representations of whatever data is being interacted with in the file system. Same thing with obviously managing whatever amount of RAM the CPU or the machine can handle, and making sure that obviously it's always going to be representing some stale version of what the actual data is, right? And it needs to be able to copy that into RAM, and as you are consuming that content, certainly many other hundreds of other folks are interacting with the same database, right? So obviously these database clients need to be able to manage and handle some of these inconsistencies. Also, databases need to handle, manage the inherent lags that the different data access mechanisms introduce, such as either where you're using some kind of mechanic, physical storage where you have to move ahead in a hard disk, or this is a flash memory, right? So there's a lot of caching that allows you to improve the performance, and so we'll talk about some of these optimizations. and how caching can help improve performance. Right, and again, as I mentioned earlier, whenever you're looking at a piece of content, it's always going to be some stale representation of the real data, and how do you handle any inconsistency with what you're looking at and what the actual data is. Data models. What we mean by data modeling, modeling in general, we mean some abstract representation of some real life phenomena, right? And different different industries, different different depending on which industry you're in, you'll have different techniques of representing real phenomena. If you're in the sciences, mechanical engineering or chemistry, whatnot, you'll have all sorts of formula that are models that represent some physical phenomenon. Yes, and you plug in the variables, and it will calculate something for you, and that will be some abstract representation of some real phenomena. We, as a data scientist, right, that usually our representation, our models are, attributes and variables, and relationships between those variables and the structure of that data. Yes. And depending on the particular domain that you're in, your model might be different, right? Depending on again, if you're a Ford Motor Company and you want to model a car, well, it will be a very sophisticated model, right? Because you're very interested in the structure of that car. If you're in a university setting, a car representation, the way you model a car might be just a make, year, and color, and a license plate, and that's it. You're good, right? So the model, will depend on which domain that you're in, or what problem you're trying to solve, right? If you want to try modeling gravity, well, it depends. If this is a game, then gravity is very important to you. If what kind of game you're in, so it would be very accurate or not. So data modeling is the science of us deciding how to structure our data, and schema is usually a how we represent that data in some physical form in particular databases, right? So we'll be creating schemas, database schemas, and that schema will have tables. Tables will have a structure and fields and data types. Obviously, there's quite a level of abstraction. The way you actually represent this in the file system. Obviously there will be probably some binary representation where you have multiple tables, multiple schema. Each schema may be in a different file, and if you have indices in these databases, probably you'll have additional files for every index, right? So that obviously will be probably vendor specific, and each vendor will have its own way of representing it to the raw file system, and how it manages the file system. Usually we're not interested, in going that low a representation. Typically we're interested in a higher level of representation, probably up to the relational model, right? On deciding that the way we model data in a relational database is through tables and foreign keys and primary keys and fields and whatnot. Yes. Right. So file system is we're physically storage in the file system. Your relational model deciding that our abstraction layer is tables, fields, primary keys, foreign keys, and whatnot in the relationships. So the file system, obviously that will be vendor specific. It could be binary, it could be a CSV file, it could be whatever the vendor decides. Whether they decide to use one record, if you choose a CSV file, one record per line, maybe that's the choice. And obviously there'll be all the IO that involved with dealing with the physical representation. And before databases, it might have been the case, right, where you have records, perhaps stored one record per line, right, and you would write perhaps some code to read this file, extract the data, and parse it, and create some high level representation in some class or instance in memory. again, once you've written this a couple of times, says, wait a minute, can I abstract this, right? And that's exactly what databases did for us, right? It abstracted these kinds of file processing drudgery, right, and abstracted it in things that allow us to do select statements, right? Select for me, retrieve all the students that are going to graduate in 1997, right? So we like to be able to do that. Select star, from student where graduating grad year is 1997. So the conceptual model allows us to think about this data in a much higher level and not deal with the details of how the data is actually structured, how it is actually stored in memory. We might say that students, there's a table of students, and it has fields such as graduating year, major, student names, and whatnot, and then you can do queries against it. There are many other data models that we're not going to cover. There's graph models. There's object-oriented. Well, actually, no, we will do object-oriented model. But there's hierarchical models such as XML. There's also real-time databases, spatial databases. There's many different ways that are specific to different types of problems, right? We're not going to do spatial databases, although there's enough interest. Maybe we could chat a little bit about that. And real-time databases as well, right? Where you have a rolling window of data that you're measuring on the field, right? And you want to have all sorts of aggregations that you might want to do in operations on real-time data. That's also a topic that might be of interest. I don't know. But we will cover object-oriented models. We'll cover hierarchical models. And conceptual models. We'll talk about UML. Will be one of the ones we cover most in this class, as being able to think about the data structure, the structure of the data, in a conceptual form, right? So that we can abstract from whatever data representation we're actually deciding on, which in particular will be relational database. But we'd like to abstract that and say, well, let's use a UML. Let's think about it graphically, so that perhaps it's applicable to other folks that are not knowledgeable of relational databases, but they might be knowledgeable in other fields, right? In object-oriented programming and whatnot. So we'll talk about a lot of UML starting today. Yeah. So the we typically the databases will also provide mechanisms that will allow us to represent the data not as it's physically stored, right? But instead interact with the data as we would like to be convenient to us, right? It might be that we've decided, for avoiding redundancy, we might have decided to split data into 3, 4, 5 different tables, yes? All related to one another to avoid redundancy, right? We'll call this a little later, we'll call it normalization, normalizing the data, right? And we usually split data into multiple tables, but for us engineers, it's the right way of storing the data. But for non-engineers that want to query the same tables, it might be very inconvenient, right? Having them to, do all sorts of joins and grab data from one record and relate it to some other record, and then aggregate all that data for consumption, right? And usually it's a very inconvenient, especially for non-engineers or non-technical folks. So oftentimes we might provide other representations of the same data, right? But only for convenience purposes of how folks want to consume the data, right? As we might have decided to split the students in one table and the professors in another table, and the courses in another table and the sections in another table. But for the registrar's office, it's very inconvenient to go and join all these tables when they want to know, who's graduating this year, and so the query might be that you have to join the students with a particular grades and enrollments, right? And with whatever grades they actually got and whatnot, right? And so usually databases will provide us things such as views, that allow us to automate and provide these convenient ways of consuming the data. And so they'll provide like a third level architecture that will allow us to provide a different ways of interacting with it. Right. So right, you have this physical schema where you have actual file system that might have the actual data plus all sorts of indices that to optimize specific queries. You have this conceptual representation of the various tables that we've normalized our data. But then, depending whether you're the registrars or the dean's office, they might want to consume this data in a particular way. For them, like the student information might capture data from the student, from the enrollment, from the section, and aggregate it into a single view, right? But we don't want to, that would have been a non-normalized representation, right? Which would have introduced some redundancy. So databases typically provide those kinds of ways of accessing. It's also a very convenient, even for regular data access. It's also typical to provide a isolate the direct access to tables, right, by providing views that allow you to read from them, right, without giving physical access to the actual tables, right? So a way of protecting or having a gatekeeper of who has access to these tables, right? And usually we provide a different layer of views that allow us to control this gatekeeping of the actual data that we're accessing.